All right, let's go. So I don't think I really have any announcements today. Let's just jump right into it. So today we're talking about testing, and have been exposed to a bit of testing already in the Problem Set Zero handout, for example. Hopefully you've all taken advantage of these. I don't know, I don't remember how much I highlighted them in lecture, if I did. But we had these tests in the handout. I think I did mention them a little. Anyway, so we had these tests, and you were able to run them to be able to test your code before submitting to Autolab. And we had extra tests. Once you finished the rest of the methods, you would uncomment these and submit again. So we've been giving tests. We've been providing them. Today's the day where we go through what's actually happening here, the structure of these tests, and how to write your own. Because let's get back to the website. In problem set 3, this is the first problem set. Problem sets 3 and 4 are the only problem sets where you'll be writing your own tests. So for these ones, you will be required to write your own tests. We'll tell you exactly what parts of the assignment you have to test. It won't always be every single method, every single piece of functionality, but you do have to write your own tests for certain functionality of the problem set. So today we have to figure out how to write those tests. We'll talk about all of the structure, everything that goes into that. So with that set up as our roadmap, let's do it. Learning how to do testing. Hey, we got it. The shortcuts for full screen are different on a lot of different apps, but we got it. Because I think this is presentation mode, not full screen. It doesn't matter. But this is our big question: is how do you know your code's correct? You sat down, you had a task, you had to write some code, and you write that code. How do you know it's right? Like, say you're on the job, an internship or a full-time job, and working as a software engineer, you get that task. Hey, write this functionality. You write it. How do you know it's right before you send it off to your boss or to the end user, to the customers, and let them use it? How do you know it's right? What do you do to gain confidence that your code is actually correct without just saying, well, I feel like it's right. I mean, I wrote it. It's got to be right. And there's kind of a progression you go through in testing your code of how you know it's right. The very first thing in 115, well, let me just submit it. Let me just submit my code. If I get full points on it, it must be right. Which is really, I don't know, dumb. It's what you have to do for the very first steps of your education. When you're first learning this stuff, that's part of why you come to college and have that available to you instead of just trying to guess, I don't know, is my code right? Am I doing the right thing? We give you some feedback and say, hey, your code's right, or hey, your code's wrong. And we usually do that through Autolab, through automated testing. That doesn't exist in the real world. It's just an academic crutch. And as you go through your time here, your time in college, we have to wean you off of that. We have to not let you just submit to Autolab and see if it's right. We still do that to an extent. Like in 116, we still do that quite a bit. But by the time you graduate, you have to not be reliant on Autolab at all. You have to know that your code's correct on your own, because it doesn't exist. When you go to the job, your boss isn't going to give you an Autolab grader that tells you if the code's right. Trust me, it takes a lot longer to write a grader than it does to write the code itself. If they're going to write the grader and provide that to you, they're just going to do your job for you, and you're unemployed. If you're relying on that, you can't get a job. There's no value that you're providing at that point. So the next thing that we get you to do is to write methods, write code that calls your code. And hopefully this is where you got by the end of 115. I would like to hope that everybody got to this point where you're actually calling your methods. You write a main method or a Python script. If it's not even in a main method, that's fine in Python, depending on how you have it structured in your 115. But actually calling your methods. So when you're in office hours in 115, you're having trouble with the homework, the TAs would usually say, well, you would say, I'm not getting points, like I'm not getting credit for this. And the TA would say, well, what does it do when you call it? and some students will be like, I don't know what you mean. And then the TA gets to sit down with you and teach you, show you some cool stuff, how to call your methods and how to test your methods by just calling them and printing to the screen what they return. This is an excellent start to testing. This can get you a long way, actually. You can do a lot with just writing main methods, calling your code. Even with where we're heading is formal unit testing and automation. Even with that, I'll still write main methods sometimes. This is still a tool in your toolbox. You don't want to throw this one away. Sometimes you just need a quick test without setting up a whole framework and everything like we're about to talk about. This is a very useful strategy. Just call the thing and see what it returns. In 116, though, we do want to go to the full automated testing. So we want to build, like you saw on the problem sets, the test that we give you. We want you to be able to fully automate the testing, because there's one big downside with main method testing, which there's one big problem with main method testing is that it's very tedious. Very tedious to do. You have to manually verify all of the outputs, and that's pretty annoying. So what we want to do is write an automated test suite or test class, I'll probably call it in this semester, test class that's going to check your code on a lot of different inputs, and then if your code is correct on every input, it always returns the right output, then it will have passed those tests. And if it fails on even a single test case, there's a single input that we give the method and it doesn't give the right answer, then the entire method is wrong. It really is an all or nothing thing. This is what we like in software engineering. We like to demand perfection from our code. If your code isn't right on every single input, it's just wrong. Because whatever that input is, like how many of your end users are going to find that input? How are going to use the software and end up finding that input? Probably a lot. I mean, it depends on the specifics of the situation, of course, but probably a lot. If you're like, well, I wrote a method that multiplies two numbers, but whenever you multiply by 5, it gets the wrong answer. But hey, it's right on every single other number imaginable. Like, that's not a good method. That's broken. Can't use it. And I'm sure you've all used buggy software where software does get released to the public that is not correct on all inputs. We want to avoid that. We want to do everything we can to avoid it. As it turns out, that's a really hard thing to do. So buggy software does get released, unfortunately, fairly often for a multitude of reasons. I won't dive into all of them. But as programmers, we can at least do our part to try to get rid of the bugs, and that's going to be unit testing. We'll write a bunch of tests and make sure our code is correct on all of our tests before we ship it to the next level. And I'm going to do this through a very, very simple example. We'll see extremely simple examples for most of this lecture, because I don't want to get bogged down on what the code does. This code right here, it's a method. If this were to be a problem set question, I would say write a method named add5 that takes an int as a parameter and returns an int, and what it returns is the parameter int plus 5. And there it is. We can all just glance at this and know that it is correct. There's nothing wrong with this code. It's perfectly fine. And obviously you would never write a method that does this. You would just add 5 in line without having a method and a method call and a stack frame and all this stuff. But just so we have something very simple to test, I want a method where we're not getting bogged down on, okay, what does this code do? If I give you something really complex here, we're distracted by the code, but what the focus of today's lecture is on the testing. I want to focus on the testing. So the code, we all know what that does. We don't have to think about it anymore. We can focus on the testing. So let's test this thing. So first, well, let's just submit to Autolab. Autolab says we're good, so we're good. Great. But like I said, that doesn't exist in the real world. So when you have this task in the real world outside of an academic setting, how are you going to test this? Well, let's write a main method. So let's do what we would do at the end of 115. This is what you would do if your 115 were in Java, of course. You would write a main method, you would call your method a handful of times, print the results to the screen, and then verify with your eyeballs that what's printed to the screen is what you would expected it to print. So we're calling add 5 to 2, I expect 7, I got 7. Add 5 to 5, I expect 10. Add 5 to 1, I expect 6. I got 7, 10, 6 printed to the screen. So I'm feeling good, looking like my method is working. Now this is good. Like I said, there's nothing wrong with this. This is still something that probably every software engineer in the world still does on occasion. But this has huge downsides. This gets extremely tedious when we have a more complex problem. Like for adding 5, fine. Might want more test cases here, and we got to verify like 10 numbers to the screen. But that starts getting really tedious. So say your task is to write a method that sorts values, and you want to make sure that it sorts, still works, still does the right thing when you have hundreds of elements in say, an array list that you're sorting. And then you're going to you're going to create your input, call your sort method, print everything to the screen, and look through hundreds of values and make sure no value is out of order. Everything is in the right order. This is something that we're not going to test with a main method unless you're, unless that's what you're into, that you just love manually checking things. Nobody's actually going to do this. We don't want to do this. So we want to automate the testing, because when the testing gets complex, or when we're testing an entire project, you have a project with dozens or even hundreds of files of code and hundreds of thousands of lines of code, and you make a change to a method that's used throughout the entire project. Like the getHP method that we talked about earlier. You have a player class and a getHP method that's used across a whole bunch of systems, the combat system, the GUI, the visuals. It's used all over the place. The enemy AI needs to know the player's HP to maybe make decisions based on that. It's used throughout the entire program, and you make a change to that method, you have to retest everything to make sure you didn't break something, that you had some crazy chain of events that broke something somewhere else in the project. So if you have main method testing only, you got to run everybody's tests and manually verify absolutely everything. And you don't know what is expected from all those tests, so you got to go to their main methods, read up on the code, figure out what the expected values are. Hopefully they left some comments for you that says, I expect this to be printed here. But realistically, nobody's ever going to do that. What we're going to do instead is automate all of this. I want to push one button in that same situation. What I want to be able to do is set up all the tests. My whole team sets up tests to be automated. I push one single button, and all the tests run and tells me if there are any issues, if any tests failed. In fact, we go even further these days. We don't even push a button anymore. The automated testing itself is automated. So as soon as we push to the repo, we will push to, say, GitHub, we'll have the test just run automatically and let us know if we broke something. So we want to automate all of this. So we have to write tests that can be automated. That's where we're headed. And this is what it looks like. We're going to spend a while to break this down, all the syntax that we see here. But this is our setup. We're going to use a framework called JUnit. And JUnit is going to be able to structure our test cases to be able to test this with one button press. So this will be in a separate file. The class is called addTest. So we're going to go create a file, addTest.java. This was in the week 2 package. It's in the topic, well, let's jump over real quick. The topic 7_testing. That's where this lives right now. And let's break this down and see what we're looking at here. So the very first thing is our first external dependency. So we have something that needs to be imported. It's not by default included in Java, but it also isn't even in the Java library. It's not in the JDK. It's not in the Java runtime at all. This is something that doesn't exist as part of Java at all in any way, shape, or form. This JUnit testing library doesn't exist in Java. This is an external library, meaning that somebody wrote this library and made the code freely available online for us to download. We can, everybody can use this code. It's all written in Java. It's Java code. And what we need to do is go out to the good old internet, download JUnit, grab this code that they offer for free, that somebody graciously wrote and offered to all of us for free, which there's a lot of in software engineering. It's a really cool thing. We have to download that code, link it to our project, and then import it. So there's a lot that needs to happen before we can, import org.junit. Before we can even do that, there's quite a lot that needs to happen. For our purposes, this is why there's a pom.xml in all our projects. If you notice when you clone the repos, you look through the files, there's always a pom.xml in the file list, and you can look at it. There's nothing too interesting, but the biggest reason we use it is to specify the dependencies. Actually, since we can go to IntelliJ real quick, let's just check it out. So the big thing we use it for is getting JUnit installed. So this right here is going to say, hey, we have an external dependency called JUnit, and we're going to use version 4.13.2. So what's going to happen is when you clone the repo, when you clone a repo, you notice there's a few progress bars that happen on the bottom of the screen. What that's doing is IntelliJ clones the repo, notices that there's a pom.xml, and then uses a program called Maven, which is this M in the sidebar, tells you all your Maven stuff. It'll invoke a program called Maven and say, hey Maven, I found a pom.xml, go do your thing. And what Maven will do is download all of the external dependencies and get all of the code for that library that we need. So if we go, if I control click on test, I can see that I have downloaded from Maven, downloaded JUnit, and I can see all of the Java code for JUnit. It's all downloaded on my machine, and I can see all the code for everything that's defined in this library. So I actually downloaded that code, and that all happens through Maven when you clone the repo. So there's a lot of steps that need to happen, but these days the tooling's so advanced, it's so seamless, so easy to use, that IntelliJ and Maven team up and just do it all for you. So it downloads the library, links it to your project, and then you can just do import org.junit.test without really thinking about what happened behind the scenes. It just all works for you because the pom.xml was already set up in the project, and IntelliJ just does it all for you. If you ever get a problem with the import, you're trying to do import org.junit and it says symbol not found, and you get an error, the red underline underneath this import, that means something went wrong with the pom.xml. I don't see this very often anymore, just the way we present the class and set up that first week. But what used to happen whenever we saw that error is students would go to GitHub, not learn how to clone repos, which these days is so easy. You just copy a link and paste it in the right spot in IntelliJ. But students used to go be afraid of cloning repos, go to GitHub, and then copy the files one by one into a new IntelliJ project. And they wouldn't grab the pom.xml because, well, it's not code, it's not things that I'm interested in for the class, and they just wouldn't grab it. Or they would grab it, but when they're copying and pasting things over, it's, IntelliJ doesn't have a chance to really recognize what's going on because everything's just so piecemeal and all, not through the correct channels and everything. So those students would usually have errors on that. If you are having those errors, just squash your fear of cloning. It's super easy. You cut and paste a link. That's all it is. You don't really have to do much of anything. It's easier than cut and pasting every file separately. So if you do see that error, that's what's up. Something went wrong with this process. For the vast majority of you, probably all of you, you won't have any issues with that at all. You'll clone the repo, everything happens in the background automatically, and you don't have to think about this being an external library. But outside of this class, you're working on your side projects and everything, and you need to set this up yourself. You need to set up a pom.xml. And if you want more external libraries, there's something called Maven Central. There's a website called Maven Central that is a repository for all the libraries that you can import using Maven. And there are, I want to say millions of them, probably millions of them. and you can see what's out there, see what libraries you can use, and import them into your project using Maven, and use all kinds of code that's just freely available out there. It's a really cool ecosystem. So if you want to play around with that, the pom.xml, that's how we're getting our external dependencies. So for most of you, yeah, you don't have to think about that. But I do want to go on that tangent just to explain what's going on with this, because otherwise it seems like magic, and especially if you do have an issue with that, that could be a problem. And what we imported on this first line was this test annotation. So now I can use this test annotation just like our override annotation. We have our test annotation too. So we had to import that first. And here we have something, a little different syntax. We don't have to do this, but I want to do this because in 116 I do assume that you're ready for more tips and tricks and stuff like that, as opposed to 115 where you're just getting your feet wet in programming. But here is a static import. So we're going to import static, and what this does is instead of importing a class, which every single import we've seen so far has been a class, technically test is an interface, but instead of importing the whole class, what we're doing is importing one static method from a class. So from the org.junit.assert class, I want to import the assertTrue static method. So that just gives me one method imported from this class. The reason for this is to avoid doing assert.assertTrue. So if we just do import org.junit assert and import the entire class, we can still do that. But then whenever we call assertTrue, we'd have to do assert, the class, dot assertTrue, call this static method from the assert class. And we saw that syntax a few times. Files.readAllLines, paths dot get, I think it is, problem set 0.average. We've seen that syntax quite a bit. If you don't want to have to specify the class name every single time you call the method, you can do a static import and just import the static method that you are interested in this case, assertTrue. So it just cleans up the syntax here. With asserts, we typically write a lot of asserts. So writing assert dot at the beginning of every single one of them just gets tedious. It's just more typing. So a static import gets rid of that. And for our test itself, we have to annotate. We have to use that annotation that we imported. So the test annotation gives JUnit a heads up that says, hey, this is a test. This method is a test method. So when I run JUnit and want to automate all my testing, this is one of the methods that should be used for that testing. Don't forget your test annotations. If you forget your test annotation, you don't have a test. You have to have the annotation for that method to be considered a test. And the big reason for this is that we do want helper methods in our tests. Sometimes we will see by the end of today a helper method in a test. So we do want some methods in these test classes that themselves are not tests. So for those helper methods, we just don't use the test annotation. But for any of our methods that are tests, we use the test annotation. So don't forget your test annotations. Forgetting your test annotations is not so common anymore, but used to be a pretty common issue in Autolab. A student will submit to Autolab and completely fail the testing portion of Autolab, and it's because they didn't put any test annotations, so they actually didn't have any tests according to JUnit, and there was nothing to run, and then everything breaks. I think if you have no tests at all, you get initialization error in Autolab. So if you see that, double check your test annotations. A test, don't forget your test annotations. So a test method will have a name equivalent to whatever name you give the method. So I'm writing a test named testadd5 at this point. Whatever you want to name your method, that's the name of your test. And I do recommend, I won't die on this hill, but I do recommend giving your tests meaningful names. And we do give some feedback, especially if something goes wrong with your test. We'll give some feedback in Autolab based on your test names. We'll say testadd5 was good, but testadd6 was bad or whatever. You'll see when we get to that point when you start submitting. But we will give you some feedback based on your test names. So if your tests are named test1, test2, test3, test4, It just introduces an extra step for you to go, wait, there was a problem with test 3. Which one was test 3 again? You got to go back to your code and cross-reference. It just adds a few more steps to your process, which is more work than just giving a meaningful name to your test. Usually just the word test and then whatever you're testing. And once we get to, well, you'll see as we go, but once you get into more specific test cases, adding some extra annotation to say this is the test, this is what I'm testing in this specific one. So having good test names here. Also in IntelliJ, you'll get your breakdown, your feedback based on test names. So it just makes your life easier. Just like having good variable names can make it easier to reason about your code. Just less cognitive load thinking about everything. And your test methods are public, void, and take no parameters. Your test methods have to take no parameters. That's what JUnit's expecting. That's what you got to do. No parameters. And notice that this is not static. These are not static methods. I'll just table that one for now, but just notice that it's not static. Then we're finally ready to actually write some test cases. So with test cases here, I'm using assert true. Assert true is this is your sledgehammer. This will always work. Whatever you're trying to assert, you can always use assert true. There are other ones we'll talk about, assert equals primarily. But assert true, you have to know how to use this one because this will always be able to do what you want to do. The other ones we talk about, assert equals, won't always do exactly what you want to do. It can't always be used, but assert true can. So assert true, the most important one to learn, takes a Boolean expression. Let me make sure I'm not getting ahead of my slides. I am. Assert true is going to take a Boolean expression and assert that the expression resolves to true. So assert true takes a Boolean expression, it'll resolve the expression and check. Did the expression resolve to true? If it did, this test case passes. If it doesn't, this test case fails. And we have to pass every single test case in order for our code to pass the test. Every single test case needs to be passed. So if we fail on any one of these three, we failed the test. If we fail on one of the three or three of the three, it doesn't matter. We can't get a 67% on this method. It's all or nothing. And in fact, if a test case fails, the entire test just shuts down. So if we call add 5 on the value 2 and it doesn't return 7, the test fails immediately and the next two test cases aren't even ran because your test already failed. Like, what's the point of running anything else? Test failed. One bug is a broken method. And notice with the adder, I am using different syntax here. I am using the older syntax, I guess, adder dot add 5. So I'm calling the add 5 static method from the adder class directly. I could also do a static import here as well and just do add 5. I could do import static week2.adder.add 5 and then call add 5 directly. And by the way, I don't have my import at all. That's because these two classes live in the same package. If two classes are in the same package, they are automatically imported. But once you have two classes that live in different packages, then you have to import. But in the same package, all the classes in a single package can see each other just fine without imports. So we want no bugs. And I said that this isn't static. I said I'd table it, tabling it till right now I'm taking that off the table. So this is not static. And also there's no main method for this file. But if I go to IntelliJ and go to run this test, I get a go button and I can run this test. Spoilers for the rest of the lecture, I guess. I can run this test and this is what it looks like when you run a test that passes. I got a green check mark. Everything's fine. That means my test passed. If I break my test and run it again, this is what you're going to see. You get this yellow X and it says the test failed at line 12. If I click on this, it takes me right to the line that cause an assert to fail, and it's this one as we would expect. But there's no static here and no main method. So I get this nice go button. I can just run this. But this isn't a main method. And I made a big deal earlier in the semester and every single trace that we ever do that every single Java program ever since the dawn of time has started with a main method. But here we're just running a non-static method which needs a class and running it without even a main method. This is weird. This is strange. This is a crazy thing that's happening. So what's actually happening, let me set a breakpoint at the first test of my method, first line of my method, and run this in the debugger, and we can see what's actually happening here. So when I run this, I have my test add 5 stack frame, which does have a reference to an add test object. Because it's non-static, it has to have a reference to an add test, which isn't a really interesting object, but it does exist. So somehow I did get an object of type add test, and if I look at my stack, I have a ton of stack frames here. I have lots of stack frames on the stack right now. A lot of them. So what actually happens when you hit that go button for a test, let me close a few of these. I shouldn't open so many. Got my tabs all set up. So when you run a test, what's happening is you get this go button, but that's because not Java, but IntelliJ knows what's up. It says, it looks like you have some JUnit stuff going on here, and IntelliJ knows enough to know what JUnit is and gives us those go buttons. But those go buttons don't just run our code. What it does is invokes a JUnit starter. Hey, take me to the code. Oh, come on. Oh, because that's internal to IntelliJ. Oh, yeah, it's not going to take me to that code. But anyway, we can see in the stack frame, we're in a main method, line 55, in a class named JUnitStarter from com IntelliJ RT JUnit. So this is internal to IntelliJ code that's running the main method. So it does, in fact, run a main method and then goes through all of this overhead, all kinds of stuff going on in the JUnit library and internal to IntelliJ, IntelliJ's internal library. A lot of stuff going on, lots of overhead before we finally get to some code that's going to run line -1 of a lambda. Yeah, a lot of crazy stuff happening. But here, calling calling our method using reflection, it's all kinds of. I don't want to get sidetracked into what's going on. But eventually it does create an object of our class type and then calls our non-static method. So all that happens in the background. There is still a main method that still is the start of the program. It's just not in our code, and IntelliJ gives us a lot of convenience surrounding JUnit testing, which is, if you ever do JUnit testing without IntelliJ, you'll very quickly appreciate everything IntelliJ does for you, because you got to start setting up some of that structure yourself, and it's part of why we still use IntelliJ for this class. We've tried to change the editor, we've shopped around a bit, but IntelliJ makes JUnit testing so damn easy that it's just hard to switch. There's not another editor that we found so far that makes it so easy. Okay, so that's the structure of testing. That's how we create a test class that can have test methods, that has test cases. If you're keeping track of all the syntax, all the vocab. So we have kind of 3 levels of testing. A test class can have any number of test methods. We only have 1 right now, but we're about to have a few more. And each test method has as many test cases. And a test case is anytime you use an assert or assert true right now. That's our test. And this is fully automated. Instead of the main method just calling the method and printing it to the screen, we are encoding also the expected outputs and checking, did we get what we expect? Fully automated testing. So my next question that I'll ask a few times, is this enough testing? So our original question of the lecture is, how do we know if our code is correct? How do you know your code's correct? Well, I'm going to make an automated test suite using JUnit and run it, and if it passes that test class, then I feel like it's correct. But now our question becomes, is that test class strong enough? Is that test class strong enough to give you the confidence that your code is correct? Is this enough testing? So right now, hopefully you're all screaming at your monitor saying, no, that's not enough testing. You're probably more passive than that right now, but hopefully you agree at least that this is not enough testing. We have 3 small positive integers, and that's just not enough. This is what I would call the common test cases for this method. These are the test cases that your method is most likely, at least, most often. Of course, it depends on what the full project is, but most likely the most often used test cases, these small positive integers, that's just the values, the integers that come up most often just naturally. So you better test these inputs, and you better be correct on those inputs. But like every developer on the planet's going to get these ones right. There's no, like, this is the first thing like this. They take the absolute value of x first and then add 5. Now, this looks like a really silly thing to do, and don't get me wrong, it is. This is a really silly thing to do. But this is what your goal of your tests is to get rid of every possible incorrect solution. Any possible bug that a developer might write, you should be able to catch that with your test cases within reason. Somebody can always write code. If they look at your test suite, they'll write, if x equals 1000 exactly, return 0, else return x plus 5. Like, they can always write an implementation that will fail your test cases. So we're not trying to we're not trying to create a puzzle that nobody can solve or anything, but you should have any reasonable bugs covered. Any reasonable bug that a developer can write, your tests should identify that as an incorrect solution and fail it. Even when you can see your code, and this is, I think, what a lot of people miss with testing, is your tests need to be able to identify any incorrect solutions. Even if you have your code, you write return x plus 5, you write your tests, and you're like, my code's return x plus 5. It's correct. Like, why am I even bothering to test this? I don't have to test this. It's just return x plus 5, and it's obviously correct. The problem is, well, what you should do, your goal should be, your tests should be strong enough that if your tests pass, you are confident that the code is correct, even if you can't see the code. So even without looking at the code at all, you should have your tests be strong enough that, hey, if any code that you give me passes these tests, I'm feeling good about it. And when I look at these 3 inputs, I don't get that confidence. There's so many bugs that a developer might write that that will pass these 3 inputs, but ultimately be incorrect, just like taking the absolute value of x first and then adding 5 to it. And one of the big reasons why we want that criteria, why we want our test to be that strong, even when I just know my code's correct. Well, how could I write incorrect code? You want your code to be, your test to be that strong, because what very commonly happens in industry is that you write your code, you write your tests for it, you ship it, everything's fine, and then sometime down the road, at some point in time, another developer goes in and rewrites your code for whatever reason. Usually in the name of efficiency, they want to optimize your code, make it faster. Your code's right, that's fine, but it needs to be faster at some point in time. Maybe it's called millions of times throughout the run of a program, and even saving 1 millisecond would significantly decrease the runtime of the overall program. So maybe we need to optimize it. So some new dev comes in and says, oh, that add 5 method, I'm going to make that faster. Sometimes X is negative, and the way negative numbers are added, it just messes things. Whatever their stupid reasoning is that they submitted this crappy code. But they might have some reasoning, usually in the name of efficiency, where they're like, I'm going to take the absolute value first. Of course, this implementation is even slower than the original one, but some people have poor reasoning skills and they will submit crappy code. When that happens, you want your tests to be sitting there saying, hey, that code's garbage, so you don't have to waste your time going in and trying to explain to your team why taking the absolute value is stupid here. You don't want to have to waste your time. You just want your test to say, hey, that's wrong. You don't even have to get involved. It's all automated. So these tests are not strong enough because it's not going to get rid of really any incorrect solution. And so this is obviously incorrect code, but our tests are going to say that code is right. It passed all my test cases. This is weak testing. That's a strong indicator that you have very weak testing. So let's fix that. Let's add a few more larger positive integers, but more importantly, the negative values. Let's get rid of that stupid solution that takes the absolute value. So we want to add some negative inputs here. For this situation, I would call these some uncommon cases. These are some inputs that might not be the ones you'll see most often, but that you'll see, sometimes. You'll see often enough that, not 0 times. You'll see it sometimes, so they need to be tested. So let's add in these negative values and test that. And the way I'm separating this can often help is to separate these into separate tests. So I have my positive values in one test and my negative inputs in another test. And I'm making sure I have a few unique situations here, like an input that goes from negative to positive and from negative to 0. I want some tricky situations like that to make sure I'm thoroughly testing this. When you're testing your code, when you're writing test cases, it helps to come up with a strong challenge for your code. So you really want to test your code. You want to challenge your code when you're writing tests and give it some really wacky inputs that are tricky to solve, tricky to figure out, and make sure that your code is correct on all those inputs. Some developers fall into the trap of writing very softball test cases, very easy test cases for their code because they want to handle their code very delicately, probably because their code is delicate and is going to break on the trickier inputs. But that doesn't make your code better. That just means your code is wrong on the trickier inputs. You want to write tests for all the inputs, even the tricky ones, and then write code that's going to pass that test. That's our goal here. So with these tests, now that crappy absolute value method implementation, that's gone. Your tests are going to say that is an incorrect solution that doesn't add 5 to these negative values. And by splitting this into 2 separate methods, you'll see that immediately. You'll see, actually, let's jump to IntelliJ and do a little bit of coding here. So let's get rid of these ones we didn't talk about yet. But here's our test right now. We can run our tests. And if you run the arrow, hit the go button next to the class, it'll run all of your tests. But it gives us our breakdown based on the individual tests. And if we go to our adder method and change this to math.abs of 5 and rerun our tests, it's very easy at a glance to see, okay, I passed the positives, but with negatives, I failed. I can very quickly see what's going wrong. I failed the very first one, so okay, I have an issue with negative numbers. Let's look at the code. Oh yeah, because I'm taking the absolute value. Well, let's not do that, and then we can pass the tests. So having separate methods gives us more of a breakdown to see what went wrong. Instead of putting all your tests in one single method, the only thing you learn there is that the test failed. The code's wrong on something, and then you have to go through the clues, click on the link, and really start digging to be able to figure out what happened. Breaking into separate methods can often help you figure out, narrow down the problem a bit more. At least for each piece of functionality, like if for the problem set 0, you have 10 methods that you're writing. I would at least want one test method for each of the methods that I'm testing. I wouldn't want everything, test problem set 0 in one big test method. You have no idea what goes wrong if that test fails. You have to dig a bit to figure out what method was failing. Okay. And then don't forget your @test annotation on every single one of your tests. Okay, so now we're looking good. So this test passes on our solution that we believe is correct and fails this very clearly wrong solution. This is what we want, and this is how we'll test your tests in Autolab, because we have to write code that tests the accuracy of your tests. This is really how we do it. I'll talk about this a little bit more in depth in a few slides here, but this is the crux of it, is we'll take your tests and run them against a known correct solution, and your tests need to pass the correct solution. If your tests don't pass the correct solution, it means your tests are broken. You have a test case where you're checking the output, and what you're checking the output to be is not what's actually expected. It's not what the method is supposed to do. If you ever get that, you should go reread the handout, make sure you understand what the expected behavior is, and then update your tests to match that expected behavior. And then we'll have a series of incorrect solutions, intentionally incorrect solutions, and your test should fail the incorrect solutions. And let me go back. It should fail all the incorrect solutions, and this is where that demanding of perfection works to your benefit. So when your tests have to fail an incorrect solution, there's a very low bar here because you're on the other side of perfection. With the correct solution and with your own solution, you need to pass every single test case. But for the incorrect solutions, all you need to do is have a single test case that fails that solution, and then you're good to go. So if I have one single input, if I only had one negative input, that would be enough to say that this is incorrect. As long as the incorrect solution fails on at least one test case, one assert, that's all it takes. Now we know that's an incorrect solution, and your tests did their job. You identified that there is a bug. That's the goal of testing, by the way, is to identify if a bug exists. And each test case is targeting a specific bug. Here I'm targeting a bug where you don't handle negative numbers of varying sizes. If you identify the bug, that's good. The fact that this incorrect solution passes your test at 5, that's fine. As long as you have at least one test case in at least one of your test methods that fails that incorrect solution, that's all you need. You've identified that it is an incorrect solution. That's good. Autolab's happy, I'm happy. Your boss will be happy. So these are our tests, and somebody gives us this wacky business. They said, okay, you didn't like my absolute value method, so you told me I have to handle negatives. Well, I got this. Well, so if the value's positive, I still get to do what I was doing. This is what I wanted to do. So I'm still going to do that if the value's positive, because that's not going to bother anything. But I have to add this check to check if the value's negative. If the value's negative, then I'm going to take the negation of the absolute value, because for whatever reason this dev really wants to take absolute value. Maybe they got that question wrong on the SAT and now they're just hyper fixated on it. Who knows why they want to do this. But now they'll take the negation of the absolute value and add 5 to it, so that's fine. And they're like, well, it's either positive or negative. What else could it be? I'm just going to return X if it's not positive or negative. This code will pass our tests, but it is, of course, very wrong. I shouldn't say very wrong. Well, it's either wrong or it's right. There is no in between when it comes to unit testing here or methods. This code is just wrong. But our tests say that it's fine. So I would say this is not enough testing. We have one more case, one more variety of test cases that we want to check. Here's what we call our edge cases. These are the ones that we end up talking about the most in terms of testing. It's pretty easy for anyone to get the common and uncommon test cases. Uncommon, maybe you got to think a little bit, but the common ones, like people are going to get those. It's the edge cases that we talk about the most in computer science and software engineering. What are our edge cases? So these are unique situations that often require a separate conditional in our code. We'll usually need some extra code in our method. Not in this case here, we're just adding 5, who cares? But it's usually something that's going to cause some unique situation. Here I'm going to say 0 is our unique case. If you write the code properly, it's not really an edge case, but when you're doing the absolute value and whatever dev's doing all that wacky stuff, this ends up being an edge case that they have to handle separately. And it's certainly something that somebody can get wrong if they overthink the question. If they're not doing absolute value stuff, they might do something else. That's definitely something they can get wrong. So let's add this as an edge case of an input of 0. And I would argue -5 might also be an edge case, getting a result of 0. We can move that to edge cases if we wanted, but at least an input of 0. These edge cases are usually our empty values. So 0, empty string, in an empty data structure. And usually in the handouts, in this course at least, the handouts will specify what to do on edge cases. So if it's an empty array list, if it's an empty linked list, if it's an empty hash map, there will be a specific bullet point that says, if it's empty, do this. If the average of an empty array list, what is that? Well, we have to specify that in the handout and say, just return 0 in that case, if it's the edge case. And they're not always empty data structures or 0 or empty string. They can be whatever unique situation presents itself for a specific problem. Could be really anything, but it's something where we have to think of what could go wrong. For the circle engine resolving all collisions, one of the edge cases was having 2 circles of different radii, or even the same radius, where their centers are exactly the same. That would be an edge case. It could be anywhere. The center doesn't have to be 0, 0. They could be anywhere, but if you have 2 circles on top of each other, that's an edge case that needs to be handled. It usually has separate code in your implementation. Most implementations will need to handle that as a separate case in the separate conditional. And for the hard tests, we definitely test for that and make sure that you can handle 2 circles on top of each other, which is something you need to be thinking about when you're writing a method like that. You really need to be thinking about cases like that. That's what it really, in my opinion at least, that's what it means to be a software engineer, is that you're thinking about all those things that can go wrong and making sure you have nice robust code, writing test cases for that. I would like to see everyone writing at least a main method at that point, because we didn't do formal testing yet, but a main method where you put 2 circles on top of each other, run your code, and see if you go infinite. Most students write code that goes infinite on that test case. So making sure that you handle that test case is, it's kind of a big deal. It's what you need to be thinking about. It's the level of thinking that you need to have when you're approaching a problem like that of, resolving collisions with circles. Like that. And if you're ever in doubt, write lots of tests, especially if you're submitting to Autolab and Autolab's like, your tests aren't good. Write more tests. Write lots of tests. There's, people you'll get a lot of judgment, I guess. Not necessarily judgment, but your coworkers will notice and can get very mad if you don't have enough testing. But very rarely will somebody get mad if you have too many tests. They'll be like, you wrote way too many tests here. Like that's not gonna really be a thing. Just write more tests. When in doubt, write more tests. They might say, wait, you wasted time on this? You could have been doing something more productive. That's the biggest argument they could give you. But they're not. They can't really get mad if you write too many tests. But when you're writing a lot of tests, the biggest thing with writing more tests is making sure you have more variety in your test. Variety in testing goes much, much farther than just having more tests, just more volume of tests. So in this example, you could have 1,000 test cases, and testing the values 1 through 1,000, positive 1 through positive 1,000, you got 1,000 test cases, way more test cases than we have here, but your testing is ultimately much, much weaker because you didn't really add in the variety of tests. On the other hand, if you have variety of tests, you don't really need many test cases. If this were an actual problem set question, and I was testing your testing, if you have test cases of like 5, -10, and 0, if you just had 3 test cases, one of them's a positive value, one's negative, and one's 0, that's going to pass in Autolab. Like, I'm not going to get too strict in Autolab where I'm like, well, you didn't test any numbers over 100 or under -100. That would probably be enough to pass the Autolab. So variety of testing goes a much longer way. I had one student where they had trouble doing testing for a question. It was points on a, I'm blanking on the thing, points on a coordinate system. And they had, I don't know, like 5 test cases or something. And they came to me and said, Autolab doesn't like my test cases. I'm like, man, bro, write more test cases. What are you doing? You got to write more than that. So they wrote more test cases. They came to me after the next lecture. They would talk to me after lecture. And they had 100 test cases. Like, I wrote more test cases, and I'm still not getting it. Like, Autolab's still mad at me about this. Like, what the hell? And so, and I looked through their 100 test cases. Every single test case was in quadrant 1. Like, all the values were positive. I'm like, yeah, you got lots of test cases, that's great, but you need variety. You need to get, at least one in each of the 4 quadrants. And I think, furthermore, I think the Autolab would have been happy with, even with test cases all in quadrant 1, but it was 2 different points of interest, and all of their test cases were looking up and to the right also. So it wasn't just all in quadrant 1. It was all moving in the same direction as well. They didn't have any situations where the second point of interest was behind the first one, where they'd have to look backwards. So I'm like, you basically have the same test 100 times. That's not going to do it. It's all about variety, coming up with different situations to make sure that your code can handle all of these different situations. Doing the same test case 100 times, effectively the same test case, same type of test case 100 times, isn't much more useful than having that test case a single time. So lots of tests, but focus on variety over just strictly more tests. And then testing in CSE116. So I alluded to this earlier. Let's emphasize it a bit more. Is when you submit your tests to Autolab, Autolab is going to take your test and run it against a correct solution. What Autolab does is take your tests, throws away your code, or sets it aside at least for the moment, and takes just your test, just what's in the test directory, and runs it against a correct solution. So we have a known correct solution sitting on Autolab, and then we run your tests against that solution. Your tests need to pass that correct solution. So it needs to say this here is a correct solution and pass every one of your test cases. If it doesn't, everything shuts down. Autolab says, no, if you're not good on a correct solution, I'm not even continuing with this. Because you need to be correct on a correct solution. If not, then your test cases, at least one of your test cases, is completely broken. And here's one of the primary ways where separating your tests into separate methods can be very helpful. So if you fail on a correct solution, Autolab will say which test methods passed the correct solution and which test methods failed a correct solution. So if you do fail on a correct solution and you have lots of test methods, it'll tell you which method failed the correct solution, which really significantly narrows down your search. If you have all of your testing in one single method and you fail a correct solution, you have no clues. You just have to go through your entire ginormous test to try to figure out what you did wrong somewhere in there. So if you have one test method and you fail a correct solution, you got a lot of searching to do, a lot of work to do. If you pass a correct solution, Autolab will run your code on a variety of incorrect solutions. So it'll rip out the correct solution, replace it with an incorrect solution, a known buggy solution, has a known bug in it, and then we'll run your code, your tests on that incorrect solution, and your test needs to fail that incorrect solution by failing at least one of your test cases. You only need one test case for an incorrect solution to be considered incorrect that fails. So failing all the incorrect solutions. You only need one test for each incorrect solution, but you do need to fail every incorrect solution that we give. So, and we'll have incorrect solutions for all of the common bugs that developers might write. And then you need to be able to identify all those common bugs. Your tests need to be able to identify them all as bugs and fail all those incorrect solutions. If you do that, then Autolab will say your tests are good and give you all the credit for the tests. The incorrect solutions, when we test on your incorrect solutions, the way it's worded in Autolab will say, do you have tests for feature X or feature Y? Do you have tests for this feature? And this is how we're testing for that, is by using known incorrect solutions that have bugs in that feature, for that specific feature. So that's how to read your feedback in Autolab. Okay. So assert true, I said this is your sledgehammer. This will do anything you ever want it to do. If you have any testing ever throughout your entire career, you can use assert true and it'll get the job done. Sometimes it might be a little more work, but it will work for you. Anything you want to test, you can write as a Boolean expression, period. There's nothing you can't write as a Boolean expression to be able to test. Maybe you need a few Boolean expressions, maybe you need a Boolean expression in a loop, whatever, but you can use assert true for everything. If that's the only one you want to learn, go for it. But there are a few other ways, a few other ones that will make your life a little easier, sometimes harder. Can make your life a little easier. Assert equals is a big one. Assert equals takes two arguments and checks if they're equal. Those two values are equal, test case passes. If they're not equal, test case fails. Assert equals. You assert if these two things are equal. This is helpful. One, it's just, easier to write sometimes. It also handles a few things that we're about to talk about with strings and doubles. Assert equals will handle those a lot easier, can make your life a lot easier. And when assert equals fails, it will give you more feedback about what failed. So if I use assert equals and it fails, it will give me some feedback. It'll say expected 5 got whatever result is, whatever was actually returned. So it does give you more feedback in the terminal. So a lot of advantages to using assert equals. The big disadvantage is if you're not checking two things for strict equality, then you can't use it. So it won't always do what you want it to do, where assert true will. But if you do specifically have the case where you're checking two values for equality, assert equals is pretty damn handy. And finally, not type hints, hint strings. You can add for any assert true, assert equals. There's also assert null, assert not null, assert false if you want to, assert not equals. There's all kinds of asserts. You can look at the assert class. Like if you control click on the assert class, you can go through and check all the asserts available to you. Assert true, assert false. Every single one of these takes an optional first parameter that's a string, and that string will be printed to the screen if that assert fails. So we have an overloaded assert true. One just takes the Boolean expression. One takes a string in a Boolean expression. Same with assert equals. I can give it a string and two objects, or just give it two objects. So every one of these asserts, we can give it an optional string as the first parameter, or our first argument on the calling side. And we have assert equals, assert not equals, fail equals, I don't even know what that is. Fail equals, value should be different. Oh, it's private. That's why I don't know what it is. It's internal. A whole bunch of overloaded ones. Yeah, all the different assert equals. Uh, but a bunch of them available to you. I don't want to just keep scrolling through things. Let's get back to where we're at. So if this assert fails, the string will be printed. Can be helpful to give you more information, more to go off of when the test fails. Sometimes useful, sometimes not. I tend to not use these, honestly, all that much. If a test fails, I'm going to run the debugger and get all the information I want. But sometimes these can be helpful to give more context. Mostly the input. Like assert equals is going to tell you the expected output and the actual output, but not the input. It has no way of knowing what input you used, but this one I can say what the input was. So now I get the information of what was the input, what did I expect, and what did I get. It gives me all the information I could want. So if we run these, which I can comment these in now. So if we run these, here's assert equals and assert equals with a hint string. If I run them, I run the whole class here. Everything passes right now, so I don't get any extra information. Everything's the same, everything just passes. If a test passes, like, what more do you want to know? The test passed, cool. Who cares? Who cares about anything else? But if I break the code and my tests start failing, this is where all of that comes into play. Is when a test fails, now I do care. I need all the information I can get. So I want to get, whatever you can tell me. So here's add 5. It just says this failed. If assert true fails, we only know one bit of information. All the test suite knows is that this Boolean expression resolved to false instead of true. We expected it to be true, but it ended up being false. Doesn't know anything else. So all it can say is, hey, your test failed here, which you can imply that, okay, this was false and not true. Because it doesn't have a way of telling you anything else. Same with the negatives. Same with the edge case. All it can say is, hey, this failed. So I can add, I don't have an assert true with, let me add it just for the sake of example. So I can add a hint string right here. Whatever string I add, input was 7. But we got it's a little messy because we're calling the method twice, but just for the sake of example, rerun our tests. And now test add 5, I'm going to get my hint string printed. Whatever I give it as a string, that's what's going to be printed here. So now I get information. I get to know, okay, the input was not 7. My string is wrong. Input was 2, expected 7, but we got, let me actually fix this. So input was 2, expected 7, but we got 8. Now I have a lot of information to work off of. I know where to go from here. It looks like I'm off by 1. Check my method, realize I have +6 instead of +5, and fix the bug. For assert equals, so here we have assert equals 5 and result. Assert equals will give us this syntax for free. It'll treat the first argument as whatever you expect to be returned and the second argument of what was actually returned, and give you this syntax. Expected 5, actual was 6. And then we can do assert equals with a hint string. So now we still get expected and actual, and we also get our hint string. The biggest piece of information here is what the input was. So on input 0, I expected the answer to be 5. 0 plus 5 would be 5. It makes sense. But what we actually got was 6, and then I would, at that point, run the debugger and figure out why we got 6 instead of 5 when we're adding 0. And, well, there's my bug. It's because I'm adding 6 instead of 5. Let's fix that. Run it again. Pass all the tests. Which is the general strategy. Write your tests, write your code, run your tests. If the test fails, if any test cases fail, run the debugger and figure out why it failed. Step through your code and figure out what exactly went wrong, and then fix the bug. If you follow that structure, that strategy, you're going to blow through all these problem sets without much effort. I mean, I shouldn't say without much. This stuff's still hard, but significantly less effort than if you just try to do what far too many students do, is hack away at the code, try to get the code right, don't test at all, submit to Autolab until Autolab says your code's good, and then as an afterthought, write your tests. The whole point of the test is to make it easier to write code. That's why the first few problem sets would give you all the tests. Hopefully you felt like, hey, writing problem set 0 is a lot easier when I can just hit run the tests and get that immediate feedback. That should feel a lot easier than if you didn't have the test. So when you are required to write tests, I do encourage you to write the tests first before writing your code, so you have that same setup, that same situation where you can run your tests. When you write your code, run the tests. If it fails, you have the information of what exactly went wrong. Run the debugger if you need more, figure out why that went wrong, and then find your bugs and eradicate them. It can be way easier. Okay. No questions in chat today. After hour and 12 minutes, I'm going to keep on pressing on then. So let's grab the latest slides. Hopefully I fixed these slides. A few of these slides, I believe the order of the expected and actual was backwards. It might still be that way. It probably is, actually. But before we jump into that, let's do a little bit more. We're done with adder. We're done with add test. Let's do a little bit more IntelliJ work. So keeping in with the theme of the last example, I want to have very, very simple methods, so we're not bogged down with the methods themselves, what the methods are doing. I want to have very simple methods and then write tests for them so we can focus on the testing. So here I have a method named combine strings in this strings class. I'm going to combine two strings separated by a space. That's my goal, is to combine two strings. Oh, I didn't want that on screen. Doesn't matter if this is on screen, I guess, but it's not something we'll use in lecture. But I wanted a little bit more complex one, but then we got bogged down in the details, and I just want to focus on a very simple one so we can focus on testing. So concatenate the strings separated by space. That's it. I think it's because when I set it up, I had all this crap here. That's why it's not hidden. So I have my test method here, test strings. String A, hello. String B, goodbye. If I call my combined strings method, I would expect hello space goodbye. That's what the results should be. And when I hit my go button, if I hit it for the class, or if I right click and go to run, that'll run all of the methods of my test. Here I'm going to intentionally run the go button right next to my test method. What that does is just runs one single method. So I want to intentionally just run one single method here. And this should pass, but it fails. So test strings, so we got something going wrong here. Let me add a hint string here. Let me just see what the output was. And it is hello space goodbye. With no, looks like no extra white space. I suppose we can surround this in quotes just to make sure we don't have any extra, like a trailing space character or something. Plus. And no, it's literally the string hello goodbye. I have literally the string hello goodbye here. That's weird, ain't it? That's weird. Well, let's go see what we can learn in the slides. Testing strings. So this test fails. This is the one we just ran. We verified IntelliJ says this is no good. This will always 100% of the time fail. That's kind of crazy. And we did already feel this. You've been working on the problem sets, the linked lists with strings. You've already felt this. Well, actually, that's not due till Thursday. Yeah, maybe not. But those of you who are on track with things have already felt this, is that you can never use equal equal to compare two strings, in Java at least. Never, ever, ever use equal equal to compare two strings for equality. This is not what we want. And I did talk about this in an earlier lecture, I think last Thursday. I did talk about this a little bit, but let's shine a big old spotlight on this and make sure we know what's up. We can't use equal equal to compare two strings. I mean, you can, like it's legal syntax, but it's going to give you bugs. And it's going to give you bugs in a really weird way. Like sometimes you'll get away with this, sometimes you won't. You don't want to use equal equal to compare two strings in Java. Do not do it. The short answer is strings can be weird, but the longer answer is that strings are actually references to objects on the heap, and when you use equal equal on two references, what it's going to do is check, are the references equal? Because that's the values. These two values are references. So equal equal is going to compare the values. The values are references. So we're saying, do these two string references refer to the same string on the heap? That's what's being asked here. That's what equal equal does when you use it on two objects. And strings are actually objects. We pretend that they are stored by value, but they are stored by reference. So equal equal will compare the references. And sometimes, like Java's pretty sophisticated with its strings. Sometimes two strings with the same value will refer to the same string. Java will do a lot of work to try to reuse memory and not create copies of strings that have the same exact characters. They'll have the references to the same existing string instead of duplicating that memory. Sometimes. Sometimes not. In this case, I set it up in a way that it won't. It's not going to share memory between these two values. It's not going to do it. So here, equal equal is always going to return false. So what should we do instead? Always use dot equals. Always use the equals method to compare two strings. This is a static method of the string class. And now we're going to compare character by character. The equals method from the string class is going to go character by character and check if they are equal to each other. This is how we want to compare strings in Java. So instead of this, and we can, if we rewrite this a little bit, we can see exactly what's going on here. So our actual is going to be this value. Our what we expect is hello goodbye. And if I set a breakpoint right here and run the debugger, actual and expected, oh, the debugger likes to hide the references though. We can see it in the bytes though. Actual and expected are references to different strings. We got 1204 here and 1205 here. We have different values for our references. Even though we are byte for byte exactly the same, we do have different references to two different strings. So equal equal is going to say that's no good. But if we do expected dot equals actual, now we're getting character for character checks to make sure that we have all the same values in our characters, and now we pass. Now we finally pass and say, yep, those two strings are equal. And if we take a look at the equals method for strings, we're going to have a whole bunch of extra crap and stuff. But once we dig deep enough, we can see we're going to check, are they the same length? If they're not the same length, they're not the same string. And then we're going to iterate over the indices and check the two characters in both strings and make sure all the characters are the same. If they're ever not the same, we're going to return false. If we make it through this entire loop without returning false, then all the characters must be the same, so we can safely return true. If they're not the same length, return false. So it's doing what you would expect to do. You could all write this code. If I said write code that compares two strings, well, technically byte arrays at this point. But that's why we're getting the value of the string, getting the byte array and then comparing the byte arrays instead of the strings directly. But that's what equals is doing for your strings. Or you could take this a step further, and we've seen assert equals already. So you can do assert equals expected actual, and this will pass as well. So assert equals, what this actually does, assert equals is going to have the overloaded null as the hint string. So it's going to call the one with the hint string where the message is just null. And then if they are both strings, wait. If they're both strings, I gotta read this crazy Java code. If they're both strings, set the message and then throw a comparison failure. Oh, because this is only if the test fails. Oh, yeah. This is only if the test fails. So if the test passes, then we're just returning, we're getting out of there, the test passed. If the test fails, it's generating a message to be able to return, so it can say expected actual. So equals regarding null is what we're actually checking. Do the null checks, and then call is equals, which once we get to this level, we can see that we are actually just calling the equals method. So what assert equals does is calls dot equals. It calls the equals method on the objects with the extra stuff, the null checks we just saw, and some extra crap, and getting the messages and stuff. But under the hood, what it's doing is calling equals. It's calling the equals method and calling that. And by the way, if we use the equals method, equals is part of the object class. So if we use the default equals, it is just equal. So the default behavior is to compare by references if we don't provide any equals method. The string class does have an overridden equals method, which we were just, let me get back to that actually. So in the string class, I just wanted to see the override annotation. So we have this icon right here, which does mean we overrode the equals method that was inherited. So we can still see that, but I was hoping to see an override annotation. But the string class is overriding the equals method, so it's saying don't compare by reference, do this instead. Do this for your equals method, which does the character for character stuff. So the string class overrides the inherited equals method from the object class and does its own thing, which is the character for character checking. So assert equals or calling dot equals, you're going to end up with the same end result. The big difference is assert equals doesn't exist if you're not in the world of JUnit testing. So if you're in your code and not in your testing, you do have to use dot equals. That's the one you really have to know how to use. is the dot equals. So this passes, assert true with equals instead of equal equal. So dot equals the method call, not equal equal the reference comparison. And we just did it in live coding, but we can take it a step further and use assert equals instead. Give it what we expect and then what we actually get. And then if this does fail, we get the better syntax that will tell us this is what you expected, this is what you actually got. Okay, so let's see this in action. This is some code a little bit expanded from code that we've seen a while ago. It's been a while since we've seen this letter grade computer. And the last time we saw it, we just wrote a main method and did informal testing. We didn't automate anything. We're still not going to build a full test class for this. We'll have a test class, but not robust enough that that would really be acceptable. I just want to make one emphasis on this one. There is, I forget exactly what package it landed in, but there does exist a full test class for this that is nice and thorough testing. Tests a wide variety of test inputs and more formally defines what the problem statement is as well. Has invalid grades if it's less than 100 or less than 0 and greater than 100. A lot of stuff. But here, I just want to emphasize a few things. So here we added this plus minus method. We're going to say if your ones digit is greater than or equal to 7, you should get a plus modifier. If it's less than or equal to 2, you should get a minus modifier. Otherwise, you get just a blank modifier. So now we can compute full letter grades with your plus minuses. And we're doing that by grabbing just the ones digit. We use the modulo operator, give me the ones digit, and then do our checks that way. What's up, Patas? So let's rewrite that as a test class. So we have our test class, our test annotation, our test method for plus minus. And given it 95, we're just checking the plus and what lecture is about. This is JUnit testing. We're learning how JUnit testing works. So given it 95, we're checking just the plus minus modifier. With 95, we would expect empty string. So I'm checking assert equals the empty string equals the result of the method. And if it fails, I'm going to give a hint string that tells me anything I would need to know about this. Most importantly, the input. The input being 95, that's something that assert equals is not going to give me, so making sure I have that there. And 78, I should get a plus, and 51, I should get a minus, which is weird, which is a bug. We won't have time to do that lecture over the summer. That's one that gets cut, but we usually have a whole lecture that says, what the hell is an F minus for 51? That doesn't make sense. And then if you're below 60, well, we don't have to go into it all. But I'd call this a bug. 51 should be no modifier. Okay, so we run this test suite and our code passes and we're super happy. Cool. But there's one big problem with this code. There's quite a few little problems with this, but there's one huge glaring problem with this code. Is that what happens when a student gets 100 in the class? So when a student gets 100, they'll get their A, of course. But when we go to plus minus, what we're doing is grabbing the ones digit. Well, the ones digit is 0 here. That's going to fall into the minus situation, and that student who demanded perfection and got 100, got everything perfect all semester, ends up with an A minus. So we add this test case of 100. We expect a plus. That should be an A plus. They're not getting that score. They're getting an A minus instead, which is horrendous. This student demanded perfection, and we demand perfection on our tests as well. If we write a test case and our code fails it, our code is wrong. Like, it's just wrong. So we need to do something about that. So, yeah, we passed 3 out of 4 tests. You know, is is that a 75? Do we get a B? Uh, or sorry, a C? Do we get a C for that, for getting a 75%? No. We demand perfection with our tests. It's all or nothing. So we have to pass this last test. We have this edge case of 100. The big thing here, one, use either cert equals or dot equals to compare your strings. But two, your edge cases aren't always 0, empty string, empty data structure. In this case, an edge case is 100. This is something that takes an extra bit of logic in our code to handle this edge case of 100. It's not, immediately intuitive looking at the question that 100 will be an edge case. Well, maybe it is because we're all familiar with how grades work. But this is going to be one of our edge cases is 100. So we have to add a test case for that to make sure that our code is correct on that input. And then if that test case fails, we better update our code and make sure we pass on that. And as edge cases often do, we're going to need a separate conditional to be able to handle that case. It just doesn't work with the logic of how we're handling the code here. Taking modulo 10, getting the ones digit, and then checking the ones digit doesn't really work for 100. It just needs to be handled separately, so we're going to handle our edge case with a separate conditional. Okay, jump back to our code. And again, I want a very simple method, but let's shift into testing doubles. So with doubles, I have this very simple method. Times 3 is just like our add 5 method. The code itself is ridiculously simple here. A method you would never actually write. You just multiply by 3 whenever you need to. But here we're taking an input x, multiplying it by 3, and returning. So whatever you give me as an input, I'm going to return it times 3. Cool. Let's test this thing. So for my test suite, I have my class doubles tests, because we're testing the doubles class. And I have my test doubles method. I'm going to call times 3 on 0.1. I'm going to get the value y, and for good measure, I'm even going to print it to the screen. I don't want to print it to the screen, actually. I'm going to do it as a hint string. I'm going to do it as a hint string because we just talked about those a bunch. Let's see that in action. Y is a double, and I tried to give it where Java is expecting a string. So I'm going to have this little hack where I'm going to concatenate the empty string with it. So the string concatenation is going to convert my double to a string. I could also do, I'm just going to leave it as that. It works fine. And I expect the result to be 0.3. I multiplied 0.1 by 3. I expect the result to be 0.3. So I'm just going to make sure that the result is 0.3. Simple code, simple tests. What could possibly go wrong? Well, this test fails. It's about as simple as you could get. We're taking 0.1, multiplying it by 3. In fact, this doesn't even have to be across a method call. It has nothing to do with the fact that this is a method call. The strings, by the way, actually did matter that it was a method call. This one doesn't. If we have 3.0 times 0.1, you would expect that to be 0.3, but it's not. And when I print it to the screen, we can actually verify that it's not. It's not 0.3. It's 0.3, 0, 0, 0, 0, a bunch of zeros, and then a 4. We got this trailing 4 just hanging out here. So my computer didn't actually come up with the right answer when I multiplied 3 times 0.1. It's kind of weird, kind of concerning. This is actually pretty concerning for a lot of reasons. But this is expected. This is expected behavior. I know if I multiply 3 by 0.1, I will get this exact value in Java, in Python, in C++. This is just how numbers work in computers. You will always get this error right here. So let's talk about why why the hell that's the case, because that's some pretty concerning, troubling things. The whole reason we buy computers, why computers have become so popular, is because they're great at crunching numbers. Like that's what we want them to do. So if they're wrong when they crunch numbers, it's a bit concerning. But this test fails. This test definitely fails. It'll fail 100% of the time. This will always fail. The short answer, by the way, is going to be don't use equal equal for doubles, just like it was for strings. Don't use equal equal to compare strings. Don't use equal equal to compare doubles. Ever, 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 ever. But why? And also with doubles, the solution is a bit tougher. Like, what do we do about it? Spoilers, we can't just do dot equals with doubles. We got to do a bit more. But we got this exact value. That's not a surprise. That's not random. It's, that is what the answer will be. So to explain why, we do got to talk a little bit about how computers represent floating point values. So an IEEE double uses this format, which is the structure for doubles that pretty much every language uses. There's probably one obscure language that doesn't use it, so I'll say pretty much, but this is how doubles are represented in computers. It's a 64-bit representation. The exact details aren't too crucial to us in this lecture, but the important thing for us to know is that 64 is a finite number. That is less than infinity. That's what we need to know. But for a little bit more details, the 64 bits are broken down into 3 parts. 1 bit for the sign, whether it's positive or negative, a 52-bit fraction, and then an 11-bit exponent. And this is read as scientific notation, but in base 2. So we have 1 point, the fraction value, times 2 to the exponent value. So it's a way of doing scientific notation in base 2 using 64 bits. And now we have to head over into how binary works. I kind of assume you've all been at least exposed to binary a little bit, but I will start from ground zero just in case you haven't been exposed to it at all. And I am going to go ridiculously fast. I'm going to explain, I don't know, maybe a week of content in one slide really fast. If I were first introducing you to binary, I would take a lot more time here. But even if you don't follow every little detail of this, you can still understand the punchline. So with binary, we're going to use a base 2 numbering system instead of base 10 like we're used to. With base 2, we only have the values 0 and 1. And that's all a computer can understand. You may have heard that, somebody probably said that to you at some point. Computers only understand ones and zeros. That's it. Ones and zeros. Absolutely everything in a computer is ones and zeros. It's all binary. So we have to get creative when we want to represent non-binary values. We have to, do some work for that. For a base 2 number, what we have, instead of having a ones digit, a tens digit, a hundreds digit, a thousands digit like we do in base 10, then we have the digits 0 through 9 for each one of those values. That's 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. Instead, we use twos. So we have a ones digit, a twos digit, a fours digit, an eights digit, a sixteens digit, and so on. So we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And that's how we represent our binary numbers. But for our purposes today, that's your very brief intro to binary if you haven't heard that before. But for our purposes today, we have to go on the other side of the decimal because we're talking about floating point values. So on the other side, it's the same thing. Instead of the tenths digit, the hundredth digit, the thousandth digit, instead we have the halves digit, the quarters digit, the eighths digit, the 16th digit, the 32nd digit, and so on. That's how we represent fractions as decimals in base 2. It's a summation of fractions. Same way with base 10. This, to jump ahead a little bit, this would be 1/10 plus 1/100th plus 1,000th plus 1/10,000th. That's how we represent our values here. Same thing in binary, except it goes by twos. So we have the one, this is 1/2 plus 1/4. So 0.11 in binary is equivalent to 3/4 as a fraction in base 10. So in base 10 or decimal, in base 10, there are values that we cannot represent exactly as a decimal portion. This you've certainly seen in K through 12 at some point. Is if we have the value 1/3, we cannot represent that as a decimal. It cannot happen. So we can write 0.33333. Like eventually, is meant however many threes we write, it's not going to be enough because we need infinite threes to be able to write down this number exactly. At some point, we have to stop writing threes and truncate the value. So what we have here isn't exactly 1/3. It's pretty damn close to 1/3, but it's not exactly 1/3. And of course, in math class, we would write 0.3 and then the bar over to represent 3 repeating. But to get it exactly, we have to use a fraction 1/3. There are such values in binary as well. And one of those such values is, conveniently enough, or not conveniently, but the reason I set it up this way is 0.1. 0.1 cannot be represented as the sum of powers of fractions of powers of 2. It cannot happen. So when we try to use this syntax and try to add up all the fractions of 2, there's no possible way to represent 0.1. 0.1 is really easy to represent in base 10. It's just 1/10, 0.1. But in base 2, it's equivalent to 0.00011, 0011, 0011, and that 0011 repeats forever, out to infinity. So at some point, we have to stop writing down 0011 because in our case, we only have 64 total bits, which is not an infinite number. So at some point, we just have to stop writing down our values. We just can't write it down anymore. So we're going to get some approximation of 0.1 when we represent it in base 2 in this IEEE 64-bit double format. We can't represent numbers like 0.1 exactly. That's just a fact of life. So we must truncate. And this is where we see the issue we see in the code. That's what we call a truncation error. The reason that because 0.1 isn't represented exactly in our double means once we start working with it, once we start multiplying and doing repeated operations on it, that truncation error will compound and grow every time we perform an operation. So we don't get exactly the values that we're looking for and that we expect. We're going to get the values a little bit different. We're going to get that 0.00004 way at the end because of that truncation error. So we have to do something about that. The good thing for us is these truncation errors are usually really small unless we're doing a lot of number crunching. Maybe we're computing compound interest over and over and over again. Then the errors can also compound. But and for that, by the way, the answer to that is we wouldn't use doubles. Just don't use doubles for that. Use something that doesn't have the same issue. But for our doubles, we need to be able to compare doubles while taking these truncation errors into account. That's something we have to do. So what we can do is do our comparisons instead of saying do these two doubles equal each other, because most of the time two doubles will not equal each other. Never use equal to compare doubles because these truncation errors will bite you. That will cause bugs. And what's more is it'll cause bugs that are really hard to track down because maybe it passes all your test cases. Maybe all your test cases were like 0.25, which is easy to represent in a double exactly. And then once your end user started using your code, they had 0.1, just happened to be their value. So we have to handle this, and the way to handle it is by allowing some tolerance. Allowing these values to be different by some small value. I like to call that value epsilon, and I'm creating this as a private constant. We talked about both of those earlier. I don't think I want to rehash it all right now, but I'm creating a private constant, so I'm naming it in all capital letters, and then setting this to some small value that's both large enough to account for any truncation errors, but small enough that it's not going to interfere with the logic of what I'm trying to accomplish. For our purposes, in CSE116, 0.001 will be a perfectly fine value for you. If you use that for all of your testing of doubles, it's perfectly fine. But you do want to think about this. Out there in the world, you want to start thinking about what this value should be. How much error can I tolerate and should I tolerate? For example, if you're measuring the distance between atoms, well, for one, you wouldn't really be able to use a double for that anyway, but you would really want to think about what your epsilon should be. If it's 0.001 meters, it's completely useless. You're just calling everything good. If you're measuring the distance between planets, you might be able to handle an epsilon of 1,000,000 kilometers. That might be fine. It all depends on what your specific application is. For our applications, 001 is going to be fine. And then once we have that value, we say, okay, and what we're saying is, as long as two doubles are within 0.001 of each other, we're going to treat them as equal. Like, they're close enough. They're close enough that we're going to treat them as equal. So we want to check if the difference between those two values is less than our allowable tolerance. If it is, they're the same. If it's not, then these two doubles are different. And when we do this, we do want to take the absolute value of the difference. We don't want to know D1 minus D2. That's not useful information to us. We want to know the magnitude of the difference. We can find that by taking absolute value. I've seen many bugs where people forget the absolute value part of this, and that's a tremendous bug. For example, if D is 5 and D2 is 1,000,000, D1 minus D2 is about negative 1,000,000, which is way less than 0.001. Like, we're just checking if it's less than that. Yeah, this is less than. So anytime D2 is larger than D1, your test case is going to pass. It's going to say, yep, those are the same. But yeah, no, D1 and D2 are definitely not the same, but it'll pass if you forget your absolute value. Take the absolute value. Now this is about positive 1,000,000, definitely not less than epsilon. Then you're good to go. So don't forget the absolute value on these. So we're checking, is the absolute value of the difference less than my allowable tolerance? If it is, then these two doubles are effectively equal. They're within 0.001 of each other. So that's how we compare doubles. Don't use equal equal. Have some way of allowing some acceptable tolerance to be able to eliminate the truncation errors. Well, the truncation errors will still be there, but to prevent the truncation errors from causing bugs in your code. There is a much cleaner way to do this in the world of testing. Assert equals in the JUnit library. JUnit knows, like, the developers know that this comes up all the time. So the assert equals that takes two doubles actually takes a third double, which is your allowable tolerance. So you can say assert equals my two doubles, and then whatever you want for your, what I named epsilon, but whatever you want for your allowable tolerance, you can provide that as a third argument, and it'll do the same thing that we just did. The caution with that is you do still need to know how to do this, because you're not always in the world of testing. Sometimes you want, in your code itself, not in your JUnit test suite, you do want to say, if these two doubles are equal, do something else, do something else. And in that conditional, you're going to have to do this logic, math the absolute value, the difference less than some allowable tolerance, or else your truncation errors are going to cause bugs in your code itself. Here we're preventing it from causing bugs in our tests, but we also don't want bugs in our code either. So in our code, if you ever need to test two doubles for equality, don't use equal equal. Check the absolute value of the difference being less than some allowable tolerance. But whatever you do, never use equal equal to compare two doubles. Truncation errors will bite you. Sometimes they won't. if you just happen to avoid truncation errors, or if you have the same truncation error in your expected value and your actual value. You know, but that's the scariest kind of bug. The bug that's sometimes there, the very elusive bugs. You don't want those bugs in your code because they're very hard to track down. It can pass all your test cases, but be a problem out there in production. You don't want those bugs. Those ones cause headaches and sleepless nights. Allow for tolerance when comparing doubles, and you'll at least not run into that one. Okay, the rest is behavioral testing. Let's talk about behavioral testing. So actually, let me jump to the problem set a little bit. So we have to test. What's the best one to? Look at? Say the audio book. I'll just start with the first one. Song. Write test for advanced playback time. So we have a song class that has a method named advanced playback time. This is something we haven't talked about yet. This is what we'll talk about the rest of the time. Is we have a class with a non-static method that we have to test. So far, all the testing we've done is through static methods that have clear input-output behavior. If I give it this input, I expect this output. Let me just call the method, and if I get that output, then I'm happy. But here we have a class with a non-static method that we want to test, and we want to be able to test that. And some of the methods that we test, like set name, some of these methods return void. So we can't directly check if this method did what it's supposed to do. It doesn't return anything. We can't test input-output behavior, which again is what we've done so far. So what we need to switch into is behavioral testing when we want to test the behavior of objects. Because with an object, we can't check its internal state. Well, not without a getter. We can't immediately access its instance variables. We have to check all of its methods and make sure all of the methods have the behavior that we expect. So we call that behavioral testing. Do these objects behave the way I expect them to? And for this, we're done with the slides. For this, I'm going to do all live coding. I don't get as much live coding as I want, but today is one day where we'll get quite a bit in. So let's do some live coding. First, I'm just going to throw some code at you, but today is all about testing. We're going to be in the item tests class. That's where we're going to hang out. And this item test class in the repo is, we have all the tests here. I commented them out. I just got rid of them for this so we can write them from scratch. But let's take a look at what we're testing. And usually what I recommend is writing the tests first and then writing your code, something called test-driven development. It makes writing your code a lot easier if you already have the tests, if you have the test ready for you to be able to run to check if your code is correct. Just makes writing code so much easier. And especially if you have to write the tests anyway, might as well write them first and get that benefit. But here, just to have a clear idea of what we're trying to accomplish, I just have the code already here. This code, spoilers, this code is buggy. There are bugs that we will identify with our tests. But let's look through, and I'll just walk through what the expected behavior is instead of looking through like a spec sheet to figure out what the expected behavior is. Let's go through this and talk about what we're doing. So this is an item class. This is like an item in a store that can be on sale. It has a price and description and can have any number of sales. So our constructor is going to initialize description and price. Sales always initialize to an empty array list of sales. I have getter and setter for the description. Those are the first ones we'll test, our first behavioral tests, because, well, they're getters and setters. They're the simplest ones to test. A setter for price and a getter that's not just going to get the raw price in the instance variable, but we'll get the price with every sale applied. So we're iterating over the sales and making sure the sales compound multiplicatively, and then returning the final price. And I have this rounded to decimal places. This is just so the output looks clean, but I'm taking the input, multiplying by 100, rounding, and then dividing by 100. So I'm rounding effectively to 2 decimal places. So the get price should have all sales applied. A good instance where the getter isn't just strictly returning something. We are doing some processing to be able to get those sales applied. An add sale method, so we can say the value is on sale. This will work by percentages. So if I add a sale of 50, then that item should be 50% off. And these will compound multiplicatively. So if I add a sale of 50 and a second sale of 50, that item is going to be 75% off. I'll pay 25% of the original base price for that item. As opposed to compounding additively, where 250% sales would be 100% off. I'm giving away items for free. I don't want to do that. So that, they'll compound the way they should compound, multiplicatively. I also want to compute the tax. For this, it's going to take a tax rate, not a percentage. So an input of 0.1 would mean that the tax is 10%. So multiply the price by the tax rate, round it to decimal places, and return it. And finally, adding a receipt line, add the description and then the total price of that item on the receipt line, which is different than what you would expect for seeing a receipt. Usually it's the prices of all the items and then the total tax at the bottom. That's how our receipts are printed, at least in America. I suppose it could be different elsewhere. But our prices are going to include the taxes for that item. So that's the class we want to test. So let's start writing our tests for this thing. And let's do this side by side. Let's do it this way so we can take a look at the code that we're testing. So let me... no, I don't want that. I want it reversed. Item test. Item's going to take me there. If I do this. Okay. So now we can see the code that we're trying to test, just so you have a reminder of what the expected behavior is. So let's write our first behavioral test. I'm going to have my test annotation, public void, as every test needs to be. And then let's do test item description. And you can, it's up to you how fine-grained you want your test methods. You can have test methods for every single tiny piece of behavior, or sometimes I will start lumping these together. I am going to lump quite a bit, of description, like everything related to the description. I'm going to lump into one test here, at least these first 3 methods. So if I want to test the behavior of a class, the very first thing I must do is create an object of that type. So I'm going to create a new item. And what do we want to... I always get stuck on when I have to come up with an example on the fly. I always get stuck with like milk and eggs and crap. What should we sell today? I might just stick with milk and eggs. How about cereal? Cereal as the description, and then a price of, let's say, $4.50. All right. So I called the constructor, and I want to make sure that the description was set properly. And it's important to test, when you're doing behavioral testing, it's important to test every piece of functionality. So I called the constructor. I have to ask myself, what's the constructor's job? Well, it's going to initialize the description and the price. I'm not thinking about price yet. That'll be a separate test method. But if I'm thinking about description, I want to make sure that that constructor set the description properly. It's very important to me that the constructor works, that the constructor did what it's supposed to do. So I have to make sure that the description was set properly, and I can't access the description. It's private. Technically, we could use reflection and grab it. We're not doing that. The way we check the description is the getDescription getter method. We're going to get this description and make sure it returns what we expect it to return. And we can do that with an assert equals. Assert equals, what I expect is serial. And what I actually get is the item's getDescription method. And we do want to go through the getters. I mentioned reflection briefly. We don't want to do that because the getter might do some processing, like getPrice does. It might do some processing here. So if we get the instance variable, that's a lot different than the getPrice method is going to return. And we want to test the behavior, not the internal implementation. I don't care what somebody did on their private methods and instance variables. I care that the methods do what they're supposed to do. I don't really give a damn how they accomplish the goal. With my tests, I just want to make sure everything works the way it's supposed to. Does this object behave the way it's supposed to behave? That's what I'm checking. And then I also want to test the setDescription method. SetDescription, let's change this to, I don't know, Frosted Flakes. And then item dot, let me just grab this. Frosted Flakes. So I'm checking, I'm calling the constructor, making sure the constructor did its job, and also making sure getDescription does its job. And then I also want to check the setter. The setter doesn't return anything, so I can't test directly if the setter did its job. What I'm going to do is call setDescription and then call getDescription. If getDescription returns what I just set the value to, then I know that the behavior of set and getDescription combined are doing what they're supposed to be doing. If this assert fails, one of the two didn't do what it's supposed to. Probably the setter, because I already checked the getter up here. If this fails, either the constructor or the getter, something's wrong with that. But this is common with behavioral testing, is you'll need to call multiple methods for a single test, to test one single piece of behavior. And this is a good test. A common mistake I see from a lot of students is not checking the constructor. I want to make sure this string made it into the description. So but I'll see a lot of students call the constructor, call the setter, and then call the getter, and assert the getter. That's some testing, but you also have to make sure the constructor did its job. You want to make sure that that initial value of serial made it into the object as well. So make sure you're testing the constructor's initialization. Whatever the constructor is supposed to do, whatever it's responsible for, make sure it did its job as well. So now we're ready to run this test. I'm going to run the whole test suite, the whole test class. And we pass. Let's go us. And then I do always like to watch my tests fail. This is something very common. A lot of people do this. I'm no exception. I'm going to break my code intentionally and run my test again to make sure the test fails. If the test doesn't fail when I know the code is broken, then my test isn't doing its job. For example, here I broke the constructor in that exact example I just mentioned where a student forgets to check this. Like, this is going to pass. I passed these tests. I know my code is broken. It's 100% broken. I know my code is broken, but my test passed this broken code. My test did not identify this bug, which means my testing is not thorough enough. And I recommend that. Go through your code and introduce one bug at a time and make sure your code, your tests always fail. If you go through and do that, then there's just about no reason your tests aren't going to pass AutoLab. But here I'm happy with this test. I'm testing the item description. Cool. And I am going to duplicate this. Let's test item price basics. I'm going to test basic price functionality here. So with this one, I have get price and set price. So I'm going to do the same thing I did before. I'm going to expect my price to be 4.5. I haven't applied any sales, so I expect the price to just be 4.5. These are doubles, so I need some allowable tolerance. And I am going to create a constant here. I'm going to say private final double. I usually call it epsilon, but I'm going to call it tolerance, since that's what I've been calling it here, 0.001. So we're going to say if we're within 1/10 of a penny of the expected value, then I'm going to call that okay. For your application, maybe 1/10 of a penny is too much tolerance. Maybe it is, maybe it isn't, but I'm going to say 1/10 of a penny is good for our application here. Then I'm going to set the price. Let's up it to $5. Now I expect the price to be $5. Get price tolerance. So this is very basic price functionality. Same thing we did with the description. I'm going to make sure the constructor initialized the price properly, and I'm going to make sure the getter and setter are doing its job without any sales applied. Let's run our test again, make sure they both pass. And they do. Go us, we're on a roll. So let's start adding some sales to this. Let's add a sale, test item price with sale. And I can leave my initial constructor tests, like that's fine. I like to keep in extra asserts. Like there's no reason for this assert to fail because it's being tested from this test. This test is the one that's going to tell me if there's something wrong with the getters, setters, and constructor when it pertains to price. But here we want to, so I'll leave this assert here. It's redundant. It's not really necessary, but I'll leave it there. I like to leave them there. But now we want to add a sale. So item.add sale. And let's say this thing is something that's going to make my math easy, probably just 50%. Add a 50% sale. And this is where I like to have incremental tests because the sales can get complicated. I can add multiple sales to make sure they compound properly. I can do a lot of crazy stuff here. But what I want to do is make sure that I have a test. I want my test to gradually build in complexity, because if I add a 50% sale and I get this one wrong, if this test fails, then I know I'm completely screwed. Like I have a very fundamental bug in my code. Whereas if I have a test, if say I put everything in one test, I just have test item and I put all of the functionality with all kinds of crazy complex stuff all in one test and that test fails, I don't really know what went wrong. I just know something went wrong. But if I have a test that's a 50% sale and make sure I got 50% off, if that's wrong, I have a very fundamental issue. But if and then I'll also, let's just add a few tests here. But if I also have another test where I have multiple sales, if the only test I have is multiple sales, let's do 50% off. Let's do well, in the spirit of what I'm saying, let's make an expensive box of cereal $10. That makes the math a lot easier. So I want a simple test. I want my tests to be as simple as they can be to be able to check for obvious errors. I want to make sure I don't have any obvious errors, and I want to make it easy to set up my test case. So let's do 20% off, 10% off, and then another 50% off on top of that. And here's a situation where I'm not going to trust my brain. That sounds weird. Where am I? Oh my god. Why is this calculator so enormous? Oh, maybe I just had it resized? Okay. Regular size calculator. And what I'll do is punch this into a calculator. When we're making test cases, this is usually this is how I like to do them, is I'll use some other tool, importantly not my code, because if I use my code to generate test cases, whatever bug I'm testing for, I'm going to have the same bug when I generate my tests, and I'm not actually testing anything. I usually go on a longer rant about that, but I'll spare you this time. So I have 10, but I'll use a calculator, or if it's more complicated, I'll use a whole spreadsheet and compute them. But 10, I want 20% off, so times 0.8, and then times 0.9 for the 10% off, and then times 0.5 for the 50% off, so I should have 360 for my cereal. 3.6. That should be the final price if these are compounding correctly. And then let me grab this one again. Multiple call. Actually, let me not do that one yet. We didn't run these tests. So let's see how we're doing on these. We're looking good. And let's completely break our sale calculation just to make sure we're actually testing something, and both of the sales completely break. Good. Okay, so we're doing good. I promised this code had bugs, but we're not finding any yet. Our whole purpose of testing is to find bugs. So with that, you can expect that we're about to find a bug. So we have 4.5. Let me actually clean this up a little bit so this is as simple as possible. I call these feeler tests. I want the test, my first test, to be just feel things out and make sure that I don't have any really, really big bugs. And then I can get to the more complicated tests later. But what I want to do here is just call get price twice. That's all I want to do. So I have a $5 box of cereal. I'm going to put it 50% off. I'm going to get its price. It should be $2.50. I'm going to get its price again. A getter shouldn't change the state of an object at all. So I'm just going to call get price a second time. Should still be $2.50. It's just a getter. You wouldn't expect a getter to return different things. But we actually fail this test. And I'm expecting 2.5. I can see which line. It's the second one that fails, meaning the first assert did pass, or else we wouldn't have gotten to the second one. And I'm expecting 2.50, but I got $1.25. So let's set a breakpoint when I have a test case that fails. This is where I like to run the debugger. I'm going to run the debugger and figure out what went wrong. So let's go through the first one. This one gave us what we expected. So I don't expect anything to go wrong, but I'll get a feel for how my code works this way. So let's go into get price. If you ever do step into and you get two methods highlighted, you can click which one you want to go into. I definitely don't want to go to assert equals, or you can leave it up to fate. Step into again. We'll choose one of them for you. I believe it goes to the first one that's resolved, but I feel like it's sometimes out of order and doesn't do what I want it to do. So we're in the get price method of the item class. We're at item 1177. We can look at our test method here where item is 1177. And we can take a look at what this item is. So the item has a description serial, a price of $5, and one sale that's 50% off. And then two values with the glasses. Remember, the glasses mean these values are not actually on the stack right here. The only thing in the stack is the keyword this with a reference to the item at 1177. Then we're going to iterate over the sales and update the price by applying that sale price. And we're going to, there's only one sale. We're going to round to 2 decimal places. I'm not interested in the rounding code, so I'm going to step over that. And we're back into our test code. We just got the value 250 returned, and that is what we expect. So that assert passes. And now let's get into our second get price call. And at this point, we can start seeing the bug. The debugger has a way of just hitting you in the face with what the bug is. Our item is no longer $5 for a base price. It's 2.5. We're going to go through our sales and apply a sale of 50% off of 2.5 and get all the way down to 125 and then return 125 as the value. So the problem is on the second call, that sale price of 250 persisted, and on the second call, our price was now 250. The problem is when we're applying our sales, we're applying it to the instance variable itself. So we're actually changing the state of our object in a getter. A getter should just compute the sale price and return it, not update the state of the object. Here, every single time we sell one of these items, or even worse, every time somebody does a price check on this item, the sale is applied again. Eventually, we're effectively giving our cereal away for free. We're going to lose a lot of money on this one. So we don't want to do this. We want to make sure we're computing the sale without modifying the state of the object. Very important, whenever you're handling references to objects on the heap, don't make a change to that object unless that's what the method is supposed to do. Like set price, we're supposed to change the state of the object. Get price, there's no expectation that get price will change the state of that object. So let's change this. The quick way to change this is to create a temporary price variable. And just for demonstration, I'm going to name it price. So we have 2 different prices. Equals this dot price. So I'm going to grab the value of the instance variable, and then actually let me name this sale price. That's just going to be confusing if I use price twice. I'll name this sale price, and I'm going to grab the value of the instance variable, and then I'm not going to touch the instance variable again. What am I building? This is, I'm teaching JUnit. This is actually for a course, so I'm not building anything that doesn't result in a final program, but I'm just using this for education. So I'm going to grab that price, and the sale price is what I want to update. So sale price equals, gets the sale applied to it, all the sales applied to it. So now I'm not modifying my instance variable, but I am computing the sale price and then returning that price. So now I feel like I fixed the bug. Let's see. Let's rerun our tests. And this test that was failing should be passing right now. So now multiple calls, I can call this as many times as I want. My getter no longer modifies the state of the object after the last call here. After the last call here, item is still $5. That's the base price of the item. And then when I call get price, I'm computing the sale price without modifying the state of my object. And that's where I want to be. That's what I want to be doing. Okay, so I'm feeling good about get price. Let's continue on with our testing. This is where I would, now that I'm getting more confident about my sales, this is where I would really put my code to the test and add a whole bunch of sales. I guess I got 3 here. It's not that bad, but they're all whole numbers. I don't have any like 20.5, but just to prevent you watching me going through that and pulling up the calculator again, like that's what I would be doing right now, but I kind of made that point already. So let's move on to the next thing. Let's test the sales tax. So let's test item tax. Get rid of all this. So if I have a $5 item, I'm going to call compute tax. Compute tax is going to return a double. This is what I'm actually getting from the method that I'm testing. Item dot compute tax. Compute tax, and let's say the tax rate is 10%. My expected is going to be 50 cents. And then assert equals expected actual tolerance. Let's make sure our tax computation is right. Cool. So we're computing taxes right as well. Feeling good. Feeling good. So now we can start combining things. Test item tax with sale. So let's do the same thing, except let's add in our 50% sale again. So item.add sale. 50. So now our item price is going to be $2.50, and we want to pay tax on the sale price of the item, not the overall price. If you had bought something on sale and had to pay tax on the original price, you'd be pretty mad, I would hope. So now I only want to pay a quarter in tax because I'm buying a $2.50 item with 10% tax. I should be paying 25 cents. Let's test this one. This is where our tests get more complex, where we tested sales, we tested tax. Now I want to make sure tax with sales, these features start combining the way I expect them. And they don't. I expected a quarter, but I had to pay 50 cents for my cereal. So it's looking like I'm getting a tax computed on my original price. So if I look at my compute tax, I don't even really have to run the debugger on this one. If I know compute tax is giving me a higher value than I expect. If I look at this, I'm returning this dot price, the instance variable. I mean, I suppose we can. Here's actually one button last time. No, never mind. I didn't even get to do it. Yeah. Oh well. Actually, I'm going to do it anyway. The one button I didn't get to show last time we ran the debugger is the resume button. Just didn't come up naturally, but here's a case where it might. I have 2 tests that call compute tax right now, and I set a breakpoint in the compute tax method, and I actually got the test case that I'm interested in. It went right to test item with sale. So that's the one that ended up running before. Your tests don't have to run in order. This ran before test item tax. But I can click the resume button. If I got the wrong one, I'll click resume. What this does is continues running your program at full speed until it hits another breakpoint. So if I hit resume, I got into test item tax. I got over to the other test because I kept running the code until this method was called and hit my breakpoint again, and then stop my code again. I'm actually interested in the first one, so I'm going to restart the debugger. Make sure I'm in the right test. And I can see I'm doing this dot price. This dot price is 5 times tax rate, which is 0.1. Yeah, that's certainly going to return 50 cents. What I need is the tax being computed on the sale price, not the original price. So we have a way to do that already. With programming, we want to do everything we can to make our lives easier and do as little work as possible. So I already did this. I already computed the sale price and get price. So here, instead of using this dot price, I'm going to use this dot get price. Problem solved. Now stop the debugger, run my test again. Now I'm passing that. Now my tax is being computed on the sale price like I want. And this would be another good time for a more complex test. I want multiple sales, multiple taxes being computed, and just really get, go crazy with it. Make sure everything is really as robust as I need it to be. Again, in the interest of tedium, not not having you watch me just go through all that minutia. We'll skip it, but that's where that would happen. And we have one more method, receipt line. I'm going to grab this test here. And again, this is where I would create a very simple test case and then start getting more and more complicated. In the interest of time and tedium, I'm just going to go right to an item with a sale applied to it and a tax rate. So let's do cereal, $5, 50% off. That looks fine. My string actual is going to be receipt line with a 10% tax. That's fine. And then string expected is going to be, so it's the description of the item, cereal, a colon space $, and then the full price with tax included. So this is going to be a $2.50 item. So I got $2.50 plus 25 cents is going to be $2.75 for the full price of this item. So I expect $2.75 right here. And then I'll assert equals. Whatever I do, I can't use equal to compare two strings. I'll use assert equals here, or we could use dot equals. I'm going to use assert equals so I can have the printout the way I expect it to, or the way I want it to, giving me more information. And let's run this thing. And we don't get what we wanted. So we expected cereal to be $2.75. What we got was cereal being $2.50.25. That's weird. And I could run the debugger and try to go through this, but it is like we already tested get price, we already tested compute tax. We know each one of these methods is returning what it's supposed to because we already tested them. So we don't have to go into those. And the whole receipt line method is just one line. And it's also a bug that's hard to see in the debugger. So I'm just going to kind of spoil what this is. So when we run receipt line, we're going to get the description, which resolves to cereal. And then we're resolving this expression left to right. So cereal plus, since the left-hand side of the operator is a string, plus is going to be treated as string concatenation. We're going to have cereal plus the string colon space $. And then we hit, and so this whole thing resolves to cereal colon space $. We see another plus. This is also treated as string concatenation, which is a binary operator. It can only take two operands. And the right-hand side is going to be this dot get price. So price is a double, which since this is string concatenation needs to be converted to a string. And the price is going to be $2.50. So we have cereal colon space $2.50, which is what we get right here. So cereal colon space $2.50. That was concatenated. Actually, the zero won't be there. We rounded 2 decimal places, but if the second decimal place is a 0, it's not going to be there. So it's just 2.5. And then we have that string concatenated with the sales tax, which is 0.25. So then we concatenate 0.25 to the end of our cereal that was $2.50. So we got two doubles that were concatenated together as strings instead of added together as doubles, because of plus being overridden, being addition and string concatenation, we ended up with string concatenation here. So so that's what we got. The one easy way to resolve this is going back to math class, add in our parentheses. Now what's inside the parentheses is evaluated first. This is a double and a double, so the plus is treated as addition, and then left to right, this is going to be string concatenation. So if we do that, then we get our test passing, and if we set a breakpoint, we can verify that we did get serial 250. It displays the way we expect it to now. But being careful about that string concatenation when you're expecting addition can bite you. I say that because it bit me before. It took me hours to find this bug when I had it in my code, because you get those really weird looking strings. If you don't know what you're looking at, it just looks like everything's breaking apart. But yeah, it's string concatenation instead of addition. So what's happening? Either parentheses or don't do math inside your string formatting is probably the better approach. Okay. That's it. That's everything I got for today. That is testing, JUnit testing in Java. That's not everything you need for problem set 3. We still need to talk about trees, but that's testing. And now, as you're working on your other problem sets, your problem set 2 right now, this can help you with your testing here. You can go into your tests. Like we give you the tests here, but if you want to add more tests, if you're still having trouble passing your code, you can add more tests on your own as well to be able to figure out what those last bugs are, trying to find those last things. Especially when it comes to like deleting an element in zipper merge. Well, we give you the test though too. You might not need to, but if it but if those tests aren't doing it for you, you're still failing in Autolab after passing all those tests. Now you know how to write some more. So with that, that's it for me. I'll go into the office hours meeting. If I don't see you there, I'll see you Thursday. Take care, everyone.